Hey, what is up everybody, it's Ivan here. And so, in this video we'll continue trying to build / understand the self-proclaimed simplest Keras GAN that can generate faces. And so, in the last video we've essentially covered, all of the questions surrounding the data set, right? We've actually got the data successfully to our Colab notebook, and we've reprocessed it, like normalized it, in the range of values from 0 to 1, and then converted it to the TensorFlow dataset format that can be used for training. Now, in this video, I suggest that we will be, I'll try to kind of show you the architectures that I've used, that I've sort of like developed and modified small pieces of, I could say. And so in this video we're going to be talking about the architectures, parts of which were inspired by the people who are credited in the description and at the top of this notebook, and also a lot of parts that I've worked out through trial and error on different data sets. So this is kind of gonna be about the architectures of the neural networks here. Now, this whole thing is kind of called generative adversarial networks, which kind of implies, by definition, pretty much that we're going to be dealing with like two separate neural networks that are going to be trained in an adversarial way, and just like a few characteristics of each one, So the first one would be the generator, and this is the network that's actually responsible for, and stay with me on this, for like taking the random noise and converting that through convolutions and upsampling into an image. So it's basically the network that takes random noise, which is like a vector with random values, and turns that into images essentially. And the second neural network is called the Discriminator, and that guy's goal is to essentially be able to, and that guy, is able to look at both the real images and the fake images, and the fake images being the images that were generated by our generator. So the Discriminator, and it's a lot of nators here in the talking, but anyways, so the Discriminator is essentially the network that's looking during training at both the real images and the fake images, and its goal is to be able to then tell which one is real, because as it gets better at telling which ones are real, it can pass that knowledge to the generator. That guy will get better at doing fakes, then the Discriminator will have to get better at finding the fakes, and then in this adversarial training circle, hopefully both will get better, and we will get results that resemble our training data. And again, the coolest part is that the learning is actually like happening in an unsupervised way. So we just got the data, we kind of like show this data to these two neural networks, but of course more accurately we show the data to the Discriminator, and without labels it learns how to make something that's similar to what we've shown it. So that's pretty cool. But now let's actually kind of look at these two neural networks and what are the architectures. And again, the reason why I call it the simplest neural net is because it's really pretty straightforward and hopefully really readable here. So let's start with the Discriminator, the guy that looks at images and tries to classify them as being either real or fake. So the Discriminator essentially, like, it's a typical kind of neural net architecture here, with a couple of tweaks that make it better at actually passing the gradients to the generator and allowing that guy to learn. But essentially, we define the sequential model, and here we have like a bunch of convolutional layers. As you can see, it's the most typical thing ever. The amount of filters increases, by the factor of 2 over each layer. So it's like 32, 64, 128, 256, up to 512, essentially filters that we get. So, it's how kind of the typical convnets work. We increase the amount of filters while downsampling the size, and so the amount of filters is kind of like depth, and the size is kind of like the dimensions of the image, right? And so the first kind of like interesting thing here is that the downsampling that's being performed in the discriminator is not being done by max pooling, which is the way it's typically done, but it's done by essentially having this stride of 2. So here's what I mean for those of you who don't know maybe. And again, we also use the kernel size of 3, which means that the actual kernel that's that slides across the image is a 3x3 kernel, right? So like there are like 2 ways to downsample that are like most common. I mean, the most common way to downsample stuff is max pooling, where essentially you just say, that's reduces the size of image by 2 pretty much. So it's kind of how it's here, 64 by 64 and gets down to 32 by 32 by just in a region of like 4 pixels, 4 features, I guess. It picks like the one that has the most value and just leaves that one, and all the other it just throws them away pretty much, and now it's downsampling the feature maps basically. In this case, the downsampling is performed by, again, having the stride of 2, which means that the filter that the kernel, when it slides across the image, it moves across the image with the stride, which it moves like by not by 1 pixel but by 2 pixels, and so that ends up creating the similar effect. And the logic and the intuition behind this approach is basically pretty much that it helps the gradients to flow back to the generator, and it's like the whole underlying theme of this guy is that its goal is to then be able to teach the generator. So we kind of try to use the whatever methods we have, of whether it's downsampling or activations. Like for instance here, it's not just ReLU, it's leaky ReLU, which also helps with the flow of gradients because they don't vanish when the input is like, when the input is like lesser than 0 and stuff. So the whole underlying theme here is to help the gradients to flow back to the generator and to have it be able to learn from the discriminator. And so essentially this long ramble is about the fact that we use the stride of 2 as a way to downsample the feature maps in our training. Then again, as I've said, the activation is leaky ReLU to also have the gradients pass, and then we also use dropout as a way to obviously avoid overfitting. And here's kind of like the progression of how the dimensions of the feature maps change. It gets downsampled by the strides, and the amount of the filters increases here to allow for more features and all. So here's another interesting thing. When I started like looking at this architecture, it did not have a fully connected layer, but I've tried training without a fully connected layer, and I found that with a small fully connected layer stacked before the activation layer, like I think it kind of improves the outputs. And so basically I've also added like the feature maps, they get flattened, and then we use a really small densely connected layer of 64 neurons with the same leaky ReLU activation to help with the flow of the gradients and the dropout here. So yeah, again, this was kind of not in the original model, but I've tried it, and especially like this model size with not that many neurons, like from my experience, it improves the accuracy. But again, like that's kind of the point of having this thing be really readable. And I guess the series kind of tries to tell you like, hey, just like pop this notebook and play around with the layers, play around with the data, and see what you get. But it's basically, what you're looking here is like the most typical neural network architecture, and most of you probably recognize that because it's basically, hey, we'll have a bunch of convolutions, then we'll flatten them, and then we'll stack a densely connected layer and then the output layer. In our case, the output layer, as I've said, the kind of classification that the discriminator is meant to be doing is binary classification. So it's it wants to give the zeros to the fakes and ones to the real ones. So we use the sigmoid activation function that squishes the inputs to the activation layer between 0 and 1, allowing for that. So, that's the basic overview that I could give. Downsampling with strides, liquor value to help the gradients pass. This thing also to help the gradients pass. Some dropout to avoid overfitting. Batch normalization, which is also to help with the learning speeds, but it's pretty typical thing, batch normalization, right? That normalizes the, just like how we normalized, the training data to be in the range from 0 to 1. The same thing is happening here, but it normalizes the inputs not just to the, to the first layer, but throughout every layer in the network. So that's the basic overview. Bunch of connet layers, flatten them, fully connected layer, then the activation layer with like just one neuron, and the sigmoid activation function. Now let's actually get to the fun stuff, I would say, because this was something that really did not seem usual for me when I started looking at that. Because the generator, it's kind of like a conv neural network, like this typical design here, but in reverse, where if here we start and the image is the input, here the image is the output, and the input is actually that vector, that noise is the input to this network, right? And so here's what I mean, right? We start out with a densely connected layer that takes as input that vector of random values, and this vector is a 4x4 by 64. I've played around with this number, right? I've tried different variations here. The one that works best is again like a modest amount, where it's not like 4x4 by 124, but where it's just 4x4 by 64. I feel like it worked best, right? Maybe the intuition here is that leaves more room for the conv layers, for the preceding conv layers to actually build our image other than to the densely connected layer. But that's just something that I found to work. 4x4 by 64 in this case, it works. Again, then batch normalization. So it's kind of important to picture this, right? We get the densely connected layer, which is a vector, then it gets reshaped into a three-dimensional tensor, and then over that tensor we can then start performing the convolutions. But here's the actual the layer that I did not encounter before working with GANs, the appsampling layer. So again, recap, we have the densely connected layer that takes as input the random noise. We reshape that to be 4x4 by 64. We normalize the inputs to the preceding layer with batch normalization, and then we do something interesting. So remember how here we were downsampling the image, so its size was dropping from like 64 to 32 by 32, then to 16 by 16. Here we kind of want to be doing the opposite. We kind of want to be, we want to be upsampling the image such that it's actually gaining in terms of size and dropping in terms of depth, because the eventual depth that we want to have should be just like three channels for the colors, and the size that we want to have is 128 by 128. So we introduce this upsampling layer. So we upsample the image, and it turns from 4x4 by 64 into 8 by 8 by 124. And so the way this appsampling layer works, essentially, it's just like how we resize an image, right? We had like a smaller image, we resize it, it becomes more like pixely, right? Just like when we had like a really small image, we resize it, it gets more pixely, but its size increases. And that's kind of the whole way that the appsampling layer works. And so we start with this really small size of 4x4. And then it grows to be 8 by 8 via the upsampling to be 16 by 16 to be 32 by 32 to be 64 by 64 before we get to 128 by 128, where we just perform another convolution, and then the final convolution, what is it, like hits the last nail in the coffin, or what is the saying, and gives us the 128 by 128 by 3. Now, Let's look at the convolution, because here's something also that's interesting. So we start with our tensor having just the depth of 64, but then obviously after we apply the convolution with 1024 filters, right, the depth becomes 8 by 8 due to the upsampling of the size, and the depth becomes 124 because that's the amount of filters that we have in the conv layer. And also the patterns here are pretty similar, I think. You know, we start with the 124, or it's not 124, it's 1024 filters, then they just drop by a factor of 2 to be 512 to 56, 128, 64, 32, and so on. Before and so yeah, it drops like that. The kernel size is 3. It drops like that, and then when we reach the desired size of our image, we perform one other convolution that decreases the depth from 64, the amount of filters from 64 to 32, and then the final convolution here. Here's what's important here, I guess. It's the one that actually gives us the image. So we have the convolution with three filters that goes over this 128 by 128 by 32 tensor, and because of the padding, because we use the padding same everywhere, the size gets preserved. So the size only changes here with upsampling, so the size gets preserved with padding, so it stays 128 by 128. But now we get the 3 filters here. So we get the depth of 3, which basically stands for 3 RGB channels. And then we activate that with the sigmoid activation function, which essentially gives us the the activations of the pixels that are in range from 0 to 1 that we can then display and stuff. So again, this is kind of something that if you look at, I think it's pretty easy to understand, but the main kind of thing here is it's pretty much a classifier in reverse. Again, this guy starts with an image, and then it ends up with some sort of classification here. Here it starts with some sort of classification, which is random noise, which is random values vector, and then it gets, this guy here gets downsampled. Its size gets downsampled before it reaches the output. Here it gets upsampled. So a lot of cool similarities here in the ways that those guys work. And so again, the actual important stuff that I would like to point out is again that we use here a really modest size of the first densely connected layer. So it's not a lot of neurons here, but it's just 4 by 4 by 64, which is 1024 neurons here. So it's pretty modest, and we're kind of counting on most of the changes to be made by the convolutional layers, which I think helps it to generate more diverse looking faces, more like different faces other than the same face, I would say. So that's my basic overview of the architecture. After we run the self code here, we can go and build the generator, and we can look at the summary here and see the similar stuff, upsampling that's happening here before we get the 128 by 128, our desired resolution, and then the only change that's being done to this tensor here is by this convolution that just has 3 filters, and we end up because of that with 3 channels, and that's basically an image. I mean, it's pretty cool stuff, so hopefully even if my explanations are not the top level, you can still look at the code and still get it. Here's some code that I wrote that can visualize what we have here, and this guy is great, but essentially what it does is this function here, it shows the output of our generator. This guy here generates the noise, our random noise. This guy here generates it passes the image through the generator, so we get the generated image. And remember, when we pass something like that through a ConvNet, we get a 4-dimensional thing where its dimensions are 1, 128, 128, and 3. So we because we can display 4-dimensional image, we kind of like specify here that we're taking the generated image with the index of 0, which is this part here, that's the actual image. Because it's a TensorFlow tensor, we also convert it to NumPy, which is how you do it in TensorFlow 2.0, and it gives us the generated image. And right now it's gray, but if we train it, it'll be more looking like faces, and I'll show you that in a moment. And here we can go and also initialize our discriminator. And this guy is also just displaying here what happens to it when it gets, and then we pass this generated image through the discriminator, and we can observe its decision here. So it's kind of like 49%, so it's not really sure, which makes sense because it was not trained. So now let me do some training and kind of see how you know, this random noise thing will change. So you know, now I went ahead and trained it for like one epoch. So now the generator actually learned something. And so if we now rerun this code and pass, and again, one epoch, it's like, it did not train for long. So, you know, usually one like, I don't know, 50 bucks or something. But more about that in the next video, which is going to be all about training, and we'll actually train some stuff. And I'll show you a few rules of thumb of, you know, how to do training and how to like interpret the outputs in the absence of like a test data set and all that stuff. But now if we run this self code, we'll actually start, you know, getting the remember, it's only after one epoch. We'll start getting the images generated that are not just gray, but that might even like resemble faces if we're lucky enough after just one epoch. So it starts to work, and it's fascinating, you know, that you can pretty much take some noise, pass it through a bunch of convolutions and upsampling, and it may start giving you the image. And so guys, that's it for this video. Hope you enjoyed it. I hope I've been able to point out a few interesting aspects of the architectures of these neural networks. And yeah, just like smash that like button to let me know that you find this video as useful, and also subscribe to the channel to let me know that you guys are excited, and like, you know, let me know basically that you guys are getting value from these videos. And if you want to support me, ways to do that are in the description down below. And if you have any questions, please do not hesitate, just like feel free to leave them in the comment section down below. I hope you guys are staying safe and your loved ones are safe, and I'll see you in the next one.